This conference will now be recorded.
Welcome.
Should I? Okay, hello everybody. My name is Jahandar. As Dr. Shu said, I'm the senior in the previous lab that she used to be there with Dr. Roysam, the head of the EC department here at the UH. And we mostly work with the bioimage data sets like rat brain images and fluorescence imaging and biomedical data sets stuff. Previously, like 5 or 6 years ago, or let's go further back, almost 10 years ago, we used to do some image processing, and then machine learning became hot topic, like traditional machine learning stuff like SVM, regressions, and stuff like that. So we migrated to that pathway. Like Dr. Shu did her dissertation, something related to those ones. And recently, like 3 or 4 years, we have started to dig into some deep learning stuff and see what we can infer from the deep learning methods to see how we can advance the state of the art or come up with some new techniques or new results out of the data sets that you are working. So that's the whole thing. We are looking for some applications in the whole brain rat slices. We take the images. We will explain a little bit how we acquire the data set and what we are interested to discover as a pattern in that data sets. And the method that I specifically used in that I'm going to present in here is going to be deep profiling. So what I'm going to do is that I am going to gather the samples and try to profile them, but not a regular clustering method, some kind of deep method. Okay, so the way that we are going to start is that the main purpose that we are studying in our lab is to study about the concussion, because it's the main important thing. So the brain is the most important organ in the body, and we have to study what's going on if something hits to the brain and what things happen in the brain. So the concussion is the study that we are going to look at, and we are interested to see if after a traumatic brain injury something happens to the brain, what is that thing that is happening and how we can cure that. So how we can come up with some drugs to treat the problems that it's going to cause to the brain when that concussion or that fluid percussion injury happens. So the study forms in the way that we start with training some mice or rats, and not we in the UT Health, actually, biologists. So they start doing some experiments, teaching some stuff to the rats, and then after that they're going to pulse a fluid percussion injury, a controlled one with 1.5. You see the mouse? You know. Do we have the laser?
Yeah, you can just use that.
Which one?
This, I don't think they have it.
You use the mouse pointer?
You just use the mouse pointer.
Does it work? I'm using it.
It doesn't?
Oh, here. I have to go to the right.
An option to turn on the laser.
Oh, yeah, that's right. That's right. Oh, perfect. Thank you.
Recording it using
Yeah.
Oh, right. That's better, actually. Oh, okay. Perfect. Thank you. So we start, we do the experiments, and we do a pulse of a certain amount of pressure to the brain, and then we take out the brain and do some specific imaging, multiplex imaging. Have you heard about the fluorescence imaging? Are you familiar with the concept? So the basic concept of the fluorescence imaging is that we are going to pour some stains, some dyes to the tissue, that each dye is going to bind to specific part of the cell. So for example, one part is going to be the cell nuclei. One part is going to stick to just the neurons. One part is just going to stick to the astrocytes, and etc. and etc. and etc. So with that way, we do the multiplex imaging that will generate a pretty large image of the whole rat brain with multiplex channels, which means that each channel is showing the part that we are interested in. Okay, so we will have, it's a little bit small, you might not be able to see it, but we have the list of just 10 channels that we are looking here, that for example In the orange, we will have the APC, which just specifically colors the oligodendrocytes. Or, for example, in the green, we will see the neurons that you can see, for example, in here in the hippocampus region. We have the neurons that are going to show up. And in here, we can see that the region of the interest, the part that we did the injury on that part, the core of the injury, that it's going to be our region of study, our region of interest that we are looking for. Okay, so everybody clear about how we started the experiment and what the data is that we are working right now? Any questions so far? Sure.
So you taught rats tricks, took the brains out, image them, image them again?
Not images. So we teach the experiments like learning things and stuff like that, and then we apply the pressure. We control them, like seeing how we can retrieve, how the learning process is going to retrieve. Are they going to remember the same thing that they're taught or not? Or how the memory, like in the maze that we taught them to find the maze or solve the maze, are they going to solve the maze again after the injury or not? So we have different rats. We have the control one, which there is no injury. We have just the injury, and we don't treat them with any specific thing. And we have the treatment. We say that, okay, this certain drug that we developed, or we think that it's going to work, we are going to try it after that and see how the learning process is going to retry. That's the biology part. And then we are going to verify them computationally. We are going to see that, okay, what are the alterations that we can see and how it's going to be related to what we are thinking of. Okay, any other questions? Okay, so traditionally what we used to do was that, okay, we have this full brain image. The image of the brain that we are seeing has thousands, hundreds of thousands of cells. Okay, those are the main events that we are going to study on. We are going to see what the cells are going to go to the alterations, what differences are going to happen in the population, in the morphology, in the behavior, in anything that we can think. Okay, so the first thing is that we have to find these cells, right? Traditionally, with the image processing techniques, we used to do segmentation. We used to do some segmentation techniques like watershed segmentation, stuff like that, that we used to find the cells, okay? And in the certain region of interest that we are going to explain about, we used to study the population. We used to study how many neurons are dead, how many astrocytes are arise, how many oligodendrocytes the population has changed. And if they have changed, are they going to be more active? Are they going to be more passive? Are they going to proliferate? Are they going to die? And all of this information is going to help us to develop the right drug to come up with the solution to the problem, right? So traditionally, we used to do the image segmentation, but there is a problem with the segmentation. The problem with the segmentation is that the only thing that we can infer from this segmentation is just the only things that we think that we know. Like the intensity, if the cell is bright, it shows that, oh, it's bright enough, it's active, it's doing something. Or if we have some arbors, like the legs and hands of the cell, are they going to increase or decrease? And what are they talking and what are they saying these things about us? But these features were not enough for us. So assume that after 2.5 years, you might have a good idea, or the people who started to be here from the scratch, that deep features are going to give us the abstract representation, are going to give us the information that we are looking for. It might not be expressive, it might not be explainable, but it's going to discover something. It's going to find out something that was not visible before. And we are going to show that using these deep features out of the deep networks. I'm not going to go to the detail of what deep network or whatever, but just saying that instead of the intrinsic features like the intensity, like the area, like the surface, like the volume or eccentricity, and etc. If we use the deep learning and extract some features from the deep network and see what those features are going to help us in clustering and profiling the cells, is there going to be any interpretable profiling? Any meaningful data set, any meaningful population of the cell that can help us to discover something new or not? Okay, so the whole purpose is that can we perform a computationally guided biological interpretation or not? can we say that, okay, if I extract the features, if I profile them, is it going to be a meaningful population that we are looking for or not? That's the whole purpose that I'm going to conclude when I end this talk. Okay? Okay. So what we are going to do is that we are going to have our region of interest that we talked about, and we are going to have our highly multiplexed fluorescence images that we are going to have, and we are again using deep learning technique. We are using cell detection. If you are familiar with the object detection modules or object detection methods that have been developed, we have fast RCNN, we have mask RCNN, we have YOLO, we have UNet, SegNet, everything that we have seen based on these deep learning methods that have been developed, and they have been achieved the state-of-the-art results or accuracy that we are looking for. So we utilize one of those ones. That's another project that I'm not going to talk into the detail of that one, but that's one part of the deep learning that we are using in our lab to find all of these cells in the region of interest that we are looking for. So you see that these are, sorry, why the laser point went? It is loading. I don't know why it's not showing the laser. Anyways, but in the top left image, you can see that small dots. Each dot that you're seeing as a dot is one cell that it's representing some information. And for example, if I take the cell, you can see on the second image on the right, the S100. S100 is the biomarker that shows the astrocyte. Okay, so if I want to see if the astrocyte, if that cell is an astrocyte cell, I will look at the S100 channel and I will say that, oh, do I see a bright cell, a bright fluorescence in there? If there is a bright fluorescence, yes, I have the S100 channel. So I can pick the channels based on my multiplex image. We have almost 50 channels. So one image that we acquire, we just not find the cell, we find whether it's an astrocyte, is a microglia, is a S100, is a neuron, etc., and then we can say, okay, that neuron is a GABAergic neuron, is a non-GABAergic neuron. If it's an astrocyte, is it reactive, is it passive? If it's a oligodendrocyte, is it boarding, is it dying, and etc., For each one, we have the certain biomarker that we are looking for. Okay, so we can choose our biomarker and we can extract the features from the network that we might use. For this network, we can use any type of network. We can use autoencoders. We can use the CNNs and use self-supervised learning methods and extract just the deep features. For this purpose, almost 2 years ago that we did this, there was a famous network developed by Professor Mallard, Stephen Mallard, called SCATNet. It was a wavelet-based method. It had mathematical rigor, so we decided to use that one to extract the deep features based on the wavelet transforms that we can have as a form of a network. So we use the scattering network to extract the features, and these are the deep features that we are talking about. Now that we have these deep features, we are interested to see whether these deep features are going to give us some information, some interpretability or not. So we use a clustering algorithm. What clustering algorithm? We can use k-means, we can use hierarchical clustering, we can use non-parametric methods like IGMM, DPMM, and all these methods that we can have. So that was a choice. We just used the hierarchical clustering. So we used selected a method of clustering, which was the hierarchical clustering, to see if we can infer something new. So we got the clustering algorithm and we selected how many number of clusters that we have, and we saw that, okay, now that we have the clusters, there are something meaningful in these clusters that are happening. Let's see what are the meaningful things that we can have. Okay, so if I have a region that you are looking for here, let's say that my region of interest ends in here. So I removed whatever that you're seeing, whatever cell that you're seeing on the left side of the image, because the cortex is specifically what I'm looking for. Okay, and I was specifically interested for astrocytes. I wanted to see what are the population of astrocytes doing. For seeing what are the astrocytes, the biomarker related to the astrocytes were S100, as I explained before. Okay, so if I see a high S100, it shows that my cell is astrocyte. If I see a low S100, I understand that this is not astrocyte. So if I do a clustering over all of my cells, again the laser is not showing, but you can see in the dendrogram on the right, right? We start with all of the cells. If I divide it to two clusters, I will have S100 negative and S100 positive, right? So the S100 negative are non-astrocytes, which can be neurons, which can be endothelial cells, which can be oligodendrocytes, which can be other types of cells that we can have. And on the right, I will just have the astrocytes. Okay? So if you take a look a little bit closer, you can see that the concentration of the green dots are more located into the center of the injury, right? So you can see, again, the laser is not working. I might need to use this one. You can see that we have more green cells, green samples in here. It shows that most of the astrocytes are centered into the core of the injury. Okay, there might be a relationship with the astrocytes and the center of the injury that we are looking for. So astrocytes might be important after the injury happens. Okay? If it goes to the next slide.
How did you pick a time post-injury to assess?
The time that it was biologist's choice. It was 14 days after the injury. So we are not expert in designing the biology part of it, but assuming that they wanted to see the effect of the drug, what happens after they use the drug, they said that, okay, we'll use it for, we had different time lapses. We had 72 hours, we had 14 days, we had 7 days.
Response, you're looking for
Yeah, exactly. Yes. I don't know why it's not going to the next slide. It completely, yeah. Might have to close it and open it again. Okay, so far, any questions?
Yeah.
How do you identify which region is the injured region?
So when we do the injury, not with the biologists when they did it on the certain region of the cortex. Because one of the reasons we have lots of neurons in the cortex. You might have heard that what is responsible for our memory are neurons. Okay, so we want to see if we pulse something to the cortex which has the neuron, and we see, okay, what happens to the population of the neuron and how does it relate to the learning process or to the memory process? Is it going to give us some information? This is not in this one, but further when we studied, we saw that, oh, the population of the neuron drastically drops, but not specifically just the neurons. Some certain subpopulation of the neuron, GABAergic neurons, that had the effect that we tried to, okay, come up with some solution, with some thing that can heal those certain subpopulation, and we saw that, oh yeah, it's working. So by this not trial and error, but by this loop of observing what's going on and coming up with the drug, and then again observing it and designing a new experiment and doing it in a loop, we can come up with the best drug for curing, for example, the concussion or the fluid percussion injury.
I mean, but if they injure a certain part of the brain, the cortex, under the microscope, it's still difficult to find it, right? So is there a colocalization of your yellow color and another color indicate this is the region of injury?
Can you repeat your question? I don't understand what you mean exactly.
On your slides, I say
correct.
The injury is on that part.
Correct. On here, for
example. Is there
example.
a color showing that is identification of the marker of the injury?
If it goes back, it hangs up again. You mean, for example, in this region, right? In here.
Right.
Okay.
So that the big region
yes.
is all considered as the injured region.
We cannot say there. It's a fuzzy relationship that we can come up with. We cannot say, okay, this is the exact border that we are looking for. But we chose a big enough region to study that contains all the things that we are looking for, and I will explain it in just a bit to see why we take this big size. And there might be some other effects. So if the injury happens in the region like in here, if the injury happens here, it's not the only place that the effect of the injury is causing. So there might be some connections from these cells to some part in here that might be out of the interest. And we have to study those ones too. But we didn't do it for this study at this point. Okay? Oh, come on. I see something different from here than there. Okay, so far, where is it? Okay, so far we found our astrocytes. We found our astrocytes that we were interested in. The next step is that what is the relationship of this astrocyte? What happens with the subpopulation of this astrocyte? Are they all performing the same, or there are other interesting things that we can see? Okay, so what we did was that we take the S100 positive, which is the astrocyte, and we split it to 3 clusters of interest, under the assumption that the activeness of the astrocyte is of the interest. Because the astrocytes are kind of, I cannot define it pretty well, I'm not a biologist, but if there's an accident in a road, the astrocytes are the road maintenance and ambulance and stuff like that. So if an accident happens, the astrocytes come there and try to clean up everything, right? So what we were interested, we wanted to see, okay, if this cleaning up thing, this activeness, can we present it in a computational manner without giving any information? And we saw that, yeah, there is an interesting thing that we can see. If we divide the subpopulation, this astrocyte population, to 3 subpopulations, we saw that, oh, one certain subpopulation is going to be concentrated in the center of the injury. So we saw that, oh, we have lots of activation. So the cyan color that you're seeing is the GFAP biomarker, which indicates the activeness of the astrocytes, sort of. Okay, so if we have lots of GFAP, if we have lots of the cyan color, we can say that, oh, the activation of the astrocytes has been increased in that region that we are looking for. And it was true, because we saw that without giving any information of the location of the cell. There is nothing there is no information of the center of the cell compared to the other ones. The only information that you're looking here is just the deep features out of the small box that we extracted from that certain cell. Okay, so this cell, if you're looking in here, does not know anything from the next cell that it's located to. Okay. So we saw that in the core of the injury, in the center of the injury, we had very active astrocytes trying to clean up the mess and fixing the issue with the injury. And when we go a little bit farther away, we see that the astrocytes are active, but not that much active. Probably they are the ambulances on the way to cleaning up the mess or whatever. So, and when we got farther away, we saw that, okay, we still have the astrocytes, but we don't have the activation of the astrocytes, because they're in another region. They're taking charge of other responsibilities that they're going to have. So based on some computational profiling on the deep features that we extracted, we saw some biological interpretation out of the subpopulation that we were interested. And this was the first aim that we started with. We wanted to see how we can infer some biological interpretation out of it. The final results that I'm going to show you, I might have 5 to 10 minutes, right? Yeah. If it goes to the next slide. There might be some problem with the software. It's going to, I don't know. It's not going to the next one.
You were posting 20 megabyte pictures.
Some, maybe, probably, I don't know. I think so. I downscaled the image, but to keep the resolution, I might didn't do that.
Where's the mouse?
Okay, the next study that we did was that it was completely random that we came up. I'm going to confess that one. It was not planned to, but we found something interesting that it was kind of interesting to the biologists, and it's worth to study more about it. So we have the cortex. Okay. The other thing that we found out was that if you have heard of, the cortex has different layers, that each layer is responsible for some specific things. And these layers mainly are related to the neurons. So the neurons are going to let us know that how we can see these layers in the brain. Okay, but the important thing is that I think that it's working. Let me go to the, yeah.
Why the power is not connected?
But it's not just the neurons. The other population, the other cell types, all of them are talking to each other. Neurons are talking to the oligodendrocytes. How? Let's see. The way that they're connected, the neuron has a main line of connection to the other ones, the axon, that those axons are wrapped with the oligodendrocytes around them. So the oligodendrocytes are not working independently compared to the neurons. We have these relationships. Okay? I was studying on non-neuron subpopulation on oligodendrocytes and on glial cells with the specific biomarkers S100, APC, MBP, and PLP. That it's not of interest what are the, I don't know, abbreviation is. But when I was doing the same hierarchical clustering thing that I was doing, again, without providing any location information of these cells to each other, I saw that all of the cells, okay, thank you. I saw that all of the cells in the green color that you're seeing, all of these cells came up in the same group. It showed that all of these cells, based on these biomarkers that are related to the oligodendrocytes and the glial cells, have shown the similar effects, shown the similarity between each other, that they ended up in the same group that we are looking for in here. And the same happened with the red ones, that red ones came up in the same group, and again the purple ones. So it started the idea that, okay, maybe not just only the neurons are talking about the layers of the cortex. Maybe there's of an interest that we study about the oligodendrocytes and about the other glial cells that are going to have a role in separating the layers of the cortex. And again, all of this inferred by extracting the deep features of the cells and then trying to profile them, cluster them without any prior biological knowledge. So there was no prior biological knowledge on selecting these channels and performing the computation, and yet we ended up with some biological interpretation out of the results that we had. So we are investigating on other things that we can infer from as biological interpretation, and this happened after we started to deal with the deep learning. And that concludes the talk that I had today on this topic. Please feel free to ask any questions if you have. Thank you. Thank you.
Question: when you showed the RCNN, did you have to do any transfer learning, or were you able to? You have to retrain the.
That's another project, but yes, we couldn't do with the RCNN. Just it doesn't relate to this one. But with the RCNN, the problem is that if we wanted to train it on the whole brain, we didn't have enough information. So we needed to use some automatic segmentation. That's the paper is going to be released in 1 month or so. I think after we publish it, I might be able to come back here and present it again. But we did some trick on the transfer learning to train the network, because it's a huge network that we are going to have. And we did a transfer learning on that one, and we ended up with a pretty nice result on that. On the whole brain image, not whole, we cannot validate it on the whole brain, but on the hippocampus region, which is a hard region that we are going to have, we have 97% accuracy. It was pretty fascinating.
What's the baseline?
The baseline, it depends. Lots of people have done that one, but in this manner, nobody has done it, because whole brain images is not something that everybody have access to. Thankfully, we had the access. So, but with the nuclear segmentation and detection stuff, usually the state of the art is almost around 90%. Yeah, 85 to 90. Any other question? Sure.
Can we skip the segmentation, directly apply the deep features to the local images patches? and then cluster.
That's what I did in here actually. So I skipped the segmentation, but still we have to find the cells, right? So we have to find the center of the cell. The center of the cell.
Skip that stuff? Just clustering the brain regions. Right?
The brain. So still we have to come up with some input data, right? What is that input data? The region that we are going to have. How we can delineate that region. So we have to fit the atlas. I think that you're familiar with that one. Either we have to fit the atlas of the brain and separate the brain with different regions and then pass those regions to the network. There is another problem with that one. If we use that, how we can use the deep learning? Because with the deep learning, we need to have tons of data. With this small sample that you're seeing, this is small, but it almost had 10,000 cells. Okay, so we need to have some. If I want to separate this region, I will have 1, 2, 3, 4, for example, or 5 or 10 regions, right? And how many of these images can I produce to use a deep learning to extract the deep features out of it, right? Yes.
So how does your input data look like? Each cell has 4 columns, different channel of the color. What kind of input data is look like?
Let me go back to the pipeline slide. So the input, the first input to the, come on. Okay. Yeah. I hope that it's finally, yes. So when we start, we use the, okay, this animation didn't come up. These are the different channels that we expect from that region. You can see different channels are going to have different information. So the DAPI starting with is the cell biomarker, this nuclei biomarker. It was so slow that I didn't notice that I had this animation. Yeah, so each different channel, you're seeing different colors that you're going to have in here. Do you mean that one? So for each crop that we're going to take out of the cell, we will use this channel properly if we are interested. So for example, if we are interested in 100 GFAP, MVP, and PL, for example.
And so for each data point, you have 4 or 5 dimensions,
4 or 5 crops of the regional that we are looking. For example, this crop is 32 by 32 pixels. I think that I'm done. Yeah, time is running out. Sure.
What was the main challenge in terms of modeling? What kind of software you have to use, programming?
So you're asking 2 questions. Whether you're asking about the challenge or the models that we use. Yeah, modeling, mainly I use TensorFlow for modeling. This specific code was not in TensorFlow. It was in MATLAB that I used that extracted the deep features, and I implemented the hierarchical clustering and a GUI, the GUI to model all of them in MATLAB. But mainly, if you are interested in doing something related to the deep learning, you have to use something that is in Python, because we have the TensorFlow, we have the Keras, we have the PyTorch, we have all of this in the TensorFlow, in the Python. So my suggestion is Python, and I am currently using other deep learning methods, which is in the Python and which is in the TensorFlow. Regarding to the challenges, one of the main challenges is we are dealing with a massive data set. We are going to have the image, the whole brain image is 30K by 40K by 50 channels. So it's no kidding, it's almost 150 gigabytes of data. And we are just dealing with the 2D. We are going to have 3D data, it's terabytes of data. So fitting them into the memory, cropping them accordingly, and all of these are the main challenges that we can have with the data set that we are working on. Definitely, because it's not impossible to do it on a workstation. We have supercomputers clusters in the school in UH that we mainly run our code in there. It's okay. It really depends on the task that you're working. For example, for my detection, I trained it almost for 2 days. and it was 2 steps, so 2 days. Okay, and again, you cannot say there is a specific answer to a question when you're talking about the deep learning. So for example, if you're asking about, okay, I'm designing a network, how many layers I should use? 2, 10, 100? I don't know. You have to try different things and see which one works. How long should I train it? 2 days, 2 hours, or 2 years? I don't know. What you will see is that the training loss is going to decrease and decrease, and the the test loss is going to increase. That's the point that you're going to have the what was the name? The overfitting. Yeah, sorry, the overfitting that you have to stop. So it's all about just some fuzzy parameters that we are going to have. No, for this purpose, I use the meta architecture. So for the faster RCNN, I use the exception resonant V2, for example. Yeah. Learning to detect the cells, not the segmentation, bonding box detection, because I was interested in this bonding box, the 32 by 32 pixels, and then I use this bonding box to feed it to another to extract the deep features and apply the clustering on those deep features. No, that's not. So when you're talking about the deep features, for example, if you have a network, you're starting to build up layers, and in the final layer, you will have the that you're looking for. The final layer is your prediction between are the deep features that are going to discriminate between the different populations or different types of the samples that you're going to have. My samples were cell, different types for different subpopulation of the cells. That's how I get one of the in the middle layers and extracted those features and use those features for clustering.
Okay, so
One last question.
So when you mention the traditional segmentation method, you're just saying it's traditional. You are not comparing with it.
No, I'm not. Yeah, if I wanted to use, I needed to use those ones. So for one cell, if I wanted to use the traditional methods segmentation features, I needed to do the segmentation. I needed to average the intensity inside of that cell and find other, for example, the area of the cell, the eccentricity of the cell, the elongation of the cell, and etc. and just use those features for clustering, which I didn't use. Yeah. Okay, thank you everybody for
Thank you. Okay. Let's welcome our second speaker, Ziad. So Ziad currently serves as Director of Operations Analytics at Calpine, where he leads a team of data scientists, software developers, and engineers in solving business and industrial problems to influence decision-making and capital allocations. So Ziad is also the co-founder of Foundation 3.ai, a Houston startup building and deploying AI as a service for clients in various industries. So welcome, Ziad.
Dennis is here. We were looking for you, Dennis.
Yeah.
Do we have access to the internet here? So if I go
Yeah,
to
we have the
okay, once I get to that.
Yeah, once you get that, I can help with that.
Okay. We had a little boy over here. I kind of lost my punchline now. Let's see it. Okay. So we're gonna kind of do a couple of things here. We have 5 to maybe 5 to 7 slides of boring slides, just to kind of give a little bit of context what we're gonna talk about. That will go. I have already a notebook on GitHub. We'll just go through 10 minutes of code. Here's simplistic kind of model of what I'm showing here. So it's to start the slide, giving a little bit of context on when we talk about anomaly detection. So I'm gonna kind of give some background context what that is, and we'll eventually make our way to the code. Okay, so when I say anomaly detection, this is kind of fits into what we call prognostics and health monitoring for equipment. And so why is that important? So if you look at a place like Calpine, there's 80 power plants, thousands of equipments, And I usually worry about that. That means to me thousands of potential failures. So we have to kind of monitor what's happening there. We have to see, are we approaching some failure or some event, any of those equipments? So since 2013, Calpine has had something called an Orca-based model. So this is NASA-based model that's actually open source. It's nothing. It's C++. You can download. You can use it, but it's nothing fancy. It's just a KNN regressor that's passing data into a kind of alarming and thresholding on that. But we've had some issues with it, though. We've had a little bit of kind of blind spots on it. We can't do prognostics. So we can't do remaining useful life. We can't do kind of fault detection on it. And so kind of that led to, let's look into how do we improve that. What are the things we can add to it, and just kind of have a more kind of a complete or supplement or complementary for what we have. And so those were kind of like the deep learning aspect of it that we started adding in there. So I'm not going to take things for granted. I'm going to assume not everybody knows when I say anomaly detection versus fault detection. So what is anomaly detection? What we call the unknown unknowns. So you can't predict it, and when it happens, you actually don't know what it is. That's an anomaly detection. That's how we kind of define it. So an example would be here. Looking at this red dot right here, or below that, it's the value is correct, but it's contextually from a time perspective, it's an anomalous behavior. And well, we don't know. So we're not predicting when it's going to happen, but when it happens, we know exactly what it is. There's another one that I'm not showing here. It's called remaining useful life, and it's a known known. So we actually are going to predict when a fault's going to happen, and when it happens, we know exactly what happens. So those are kind of the elements of prognostics. So probably is rolling in his grave right now of how his psychology is being used here, but you can't simply talk about training if you don't have if you don't have maintenance letting happen. I've been to power plants and refineries where somebody mentioned, hey, I need to monitor this equipment, and there's not even sensors on it, or if there had sensors, they're not even collecting data out. There's no point in talking about machine learning at that point. You want to talk about the basics, the food, basically. That's kind of what I look at it here. Anomaly detection then comes in as a way to induce active learning. So if we don't know all the events, we don't know all the physics behind some of those systems. So if I have an anomalous behavior, that's actually going to feed my maintenance system to kind of basically label events. We do root cause analysis, we'll label that event, that becomes then part of the library we're going to do for fault detection. So that's kind of how those things tie up. Once you do that, then you get to that aspect of remaining useful life and kind of building prognostics. So that's kind of the context of some of this stuff. So what's right here? Yep. So from a kind of equipment framework, monitoring the equipment, what are some of the things we're going to do here? So we're going to go through a couple of things. So it's good to think about it in two layers. So there's the data science team. This is kind of the R&D team. We're sitting there building, designing what is that pipeline going to look like? What's the right model? How do we actually tune it? What's that architecture? Once that's done, we want to push it out to analysts. So those are the engineers, the people that have subdomain knowledge that will actually take this architecture, and they will basically have an interface. They can look at sensor data. They can train the model, deploy a model. They can also go back and look at actual streaming data and really perform root cause analysis and evaluate what's going on. So those are kind of the two layers of that interface. So in this discussion here, the next kind of 10-15 minutes, we're going to focus on the top one, just the data science team piece. So we're going to go through, what does that architecture look like? How we thought about it? What are kind of the process to kind of make it work? One more thing here, just this is kind of a view of like what is an analyst perspective. So this is an interface that's showing different sensors coming in. They get to QA/QC kind of the data per se, decide the filters on it. We've kind of given them a couple of knobs, guardrails for tuning the model. So give them something on dropouts, something on contamination factor. I'll explain what those mean in a minute here. And then they can kind of also play with the validation data, training data. They can actually visualize what that model is doing. And then below that, this is streaming data, live data coming in. They can see when things kind of go anomalous, basically. Okay. All right, so This is what we have right now, at least what we started with back in 2013. It's a KNN regressor. Like I said, it's a C++ based algorithm. It's written by NASA back in 2000. It was a state of the art. That's actually what NASA used for aviation industry, for aviation safety, that particular model. So you have a regressor model, KNN. We're basically modeling the input data, right? And the error from that, the residuals, we apply a threshold alarm on that. So if the residual of a temperature is, basically exceeds, either percentage or absolute value, alarm on it. You get enough of those alarms. But fast forward like about 10 years later, then there was some more kind of research done on that particular aspect, which is, let's not just apply threshold, let's do something what we're going to call one class classification. So ignore the first piece that shows this autoencoder, just ignore it for a second. Take that same KNN regressor model, take a residual on normal data, on data we think is normal, and pass it to a method called one class classification. In this case, I'm using isolation force. One class classification knows only one class. As an auto distribution of the training data, it's going to basically flag it. It's a fairly simple process to kind of work through. Isolation force is one of the methods. Support vector machines, one class classification support vector machines is another one. Local outlier factor is another one. It's based on KNN. You actually can find those in scikit-learn. They're built-in procedures for those, so you don't actually have to write from scratch if you want. But then we don't want to just do normal abnormal. We actually want to apply how this framework in general is kind of being built right now. In fact, I want to say in 2012, NASA Ames Lab came up with one class classification for, and since then nothing has beaten yet for aviation safety, and it's based on support vector machines. So you have whatever your models initially, but eventually one class classification is a support vector machine. So we're going to kind of talk a little bit here, a little bit more detail about the autoencoders, what we're doing with that. So we're doing denoised stack autoencoders. So if you're not familiar with that, so stack autoencoders, as you can see here, we got multiple layers, and each dense layer is, you stack them up, that's a stack autoencoder for you. Denoise, because what we want to do is we want the autoencoder to learn the features. So we're actually going to add noise to the data, and so that it can learn the actual important features from that. So that's what we call the denoise stack autoencoder. From a simplistic perspective, if you take every one of those dense layers right here, and you change the activation function to linear, instead of being sigmoid or tanh or ReLU, what you have here is a principal component. Just change it to this linear, then you get principal component. So said differently, an autoencoder is a nonlinear principal component. That's one kind of simplistic way to think about it. So here is an example that I'm showing for, that's been a lot of research on that particular topic, using them with sensor data. So I'm showing a window of sensor data being passed. The autoencoder, the way we're going to design it is going to be your input layer. You start kind of going down, compress it to what we call the bottleneck. And then we're going to decode back out. And we're going to reconstruct the same input signal. So it's just the same input. We're going to reconstruct it back out. And that error is what we're going to pass to that fault classification or anomaly detection after that. So why are we using kind of autoencoders? Why do we pick that versus some other methods? In this case, we have kind of a library of different methods, but this one is what's being kind of pushed as a beta version into production. So one is Summa Supervised. So it's really easy to just kind of define input-output in that sense. Your input is your output. It's fairly easy to train. So on single GPU, I can go 1 year of data, and probably with early stoppage to kind of make sure I'm not overfitting, probably about a minute, it's done, it's trained. So it's kind of fairly easy to use. But the big thing is what we call multimodal here. So I'm going to go a little bit domain knowledge here, but just kind of bear with me on this one. So if you have a vibration signal coming in from a raw data, it comes in, let's say, at 2.5 kilohertz. So that's 2,500 samples a second. You get, let's say, a valve servo signal that's current or voltage. That may come in at 1,000 or 5,000. So you take those raw signals. What we do today is we actually apply FFT to those, fast Fourier transform, You do frequency spectrum on those. You decide that I'm going to look at 500 hertz. What's the amplitude here? At 1,000 hertz, what's the amplitude? And in this kind of setup, Jahandar was talking about deep features earlier. So we're familiar with kind of doing feature extraction on images, on text, on audio. Well, this is also kind of a feature extraction on the raw signal without actually knowing the spectrum or the frequency analysis that they do an FFT on. So it allows you to actually extract the important features from that. And so you can pass the raw signal data to it as is at 2.5 kilohertz, at 5,000 hertz, and kind of pass it in. So that's kind of one useful way to do it. If there are any questions, by the way, just feel free to stop me before we get into later the code. Okay. So then the next step to that, okay, so we built an autoencoder, we did a reconstruction error on that, and we're going to pass it to an isolation force. So the way isolation force works, it's a special case of random forest model. So if you have an inlier, so a data point that looks normal, like the one on the, I guess that would be left side. On the left side, it's in a dense area, right? So it takes quite a lot of splits to isolate that point. If you look on the right side, this is an outlier data. It's not going to take many splits to isolate it. So the more splits, that's going to mean inlier. If you have less splits, that's an outlier. That's how the isolation force, in a simplistic way, how we train that model. So it's actually taken that kind of path. The longer the path, that's an inlier. The shorter the path, that's an outlier. And what I like about it, compared, so you can do the same thing with support vector machines. You can do the same thing with local outlier factor. It outperforms typically local outlier factors, which is a KNN-based method. It's on par with support vector machines, but computationally very easy to train. And so that's kind of one of the advantages of using it. Okay. So one final thought on kind of when we'll be done with the PowerPoint, just to think about this. When we think about doing hyperparameter tuning for this, I'm not thinking about just a reconstruction error, for instance, on a support on the autoencoder. We have to take it all the way through the pipeline. Meaning, how many? If I know from training data how many kind of false positives I have, or how many actually true positives that we have, we want to optimize for that. So there's a lot of things to optimize in this pipeline, including the noise we want to add to the data. How many layers we're going to have in an autoencoder, how many neurons we're going to have in there, all the way through what the isolation force hyperparameters are going to look like. So the optimization is a little trickier. It's not a straightforward one that you would do just on a deep learning network. So that's on the PowerPoint here. Any questions before we look at some code? No? Okay. So should I just go ahead and go to the next one? Okay. So what I'm going to show here, it's already on GitHub. It's people can download, people can use, no big deal. It is a kind of, I want to say, simplified version of the overall work. For reasons I'll explain in a bit here. It's not there yet. So escape and then go to that. Should I hit escape on this?
Oh, it's not. Yeah.
Oh, I see.
And move it.
Yeah, there you go. Perfect.
Okay.
Let's see if I can figure this out. All right. Yeah, I'll have to look with you guys like this. Okay, or like over here. So some things here. First of all, I'm simplifying the problem a lot. I'm not showing any 5,000 hertz or any 2.5 kilohertz data. More like simple sensor data. It's actually on a real engine. There's some real event here that did happen. So this is what we had one engine that had an event. Even when we did a playback on it with the existing method that we had with KNN, we couldn't actually see it. But when we deployed the one-class classification with random forest and also with this one here, we were able to see that event. So I'm kind of doing a reenactment of that, I guess, if you want. But it's I'm using kind of a slightly different data set. I'm hiding some things because some of that stuff is proprietary. I can't show. So we're gonna kind of go through it. So this is just a Jupyter notebook. don't judge me for the quality of the code. This is really not production level code here. So I'm not going to go through all the details. I'm assuming there are going to be a level of comfort with some of the stuff here. So the process is the following. We're going to pulling the data here, creating training and validation data set, adding the noise, designing the autoencoder layers, and then basically kind of passing the residuals to that. So the first function is just nothing but a data frame and just applying some filters to it. So we're creating a training validation data set. A neural network, I'm sure you've already learned that many, many times. The reason why I want to do training and validation is we want to score on the validation so we're not overfitting. That's just a simple thing we always want to do. So I'm just doing a splitting the data. I could have done some stratification on some variables to make it, but I did it in this case. And then I'm using Keras with TensorFlow backend. Typical thing with neural networks, you want to scale the data. I have sensors that are reading between 0 and 100. Some of them are reading more than 2,000. So I need to have them all in similar scale. And so it's just a standard scaling that I'm applying here. I'm using scikit-learn standard scaler here in this case. A couple of things I could have done with adding the noise to the input. I could have added a layer inside Keras, or I just did it on the input before passing it in. Okay, so what we're seeing here is, and this is kind of what I mentioned, the encoder is going to come in to a bottleneck, and then then you have mirror image of that. So you can see the first layer is a 50 neurons, the second one is 10. I'm just using relative activation. I get to the one that has 4. That's the bottleneck, and then we're going to mirror back out. This is kind of typical boilerplate autoencoder method that you're seeing here. So this is nothing special here. But I'm not using, if you're familiar with Keras, I'm not using the typical sequential method. I'm actually using here what they call the API. So this is kind of how we build one layer after another, because this is useful to go back and actually do some editing with it if I want to do some kind of different things with it. Okay. Again, if you're using Keras, you instantiate the model. This is when we call model XN and decode it here. And it's just a summary. This is not a very large model, just 2,000 parameters. And I'm defining an early stopping here for that. So this way we are not overfitting and doesn't need to go I don't need to train it for too long. I don't need to run 500 epochs on it. So the early stopping is just kind of, you see that minimum delta patience of 20. So that means after 20 epochs, it's not improving. You can stop and save the model. That's kind of what this is doing here for us. And just like I mentioned with autoencoders, what I'm passing is the input is the noisy data. The output is the original data. That's kind of what we're doing here. Anybody have questions, concerns with so far what we're showing code-wise? Okay, everybody's good. You can see, so obviously if you look at the line number 381.447, this has been ran many, many times. So every time, we've been reinitializing the state using. So that's why you see the loss here, showing up like not already pretty low and not improving much. That's because it's been ran many times. If you started on it from scratch, you start with like almost 1 or 2, and then it kind of goes all the way down. This didn't take long. I mean, quite honestly, it was fairly quick. This was trained on a DGX single GPU. We just used single GPU for it and trained it. After that, I'm going to just regenerate the training data here. So that's kind of, what's that training data? Build a reconstruction error on that signal. I'm going to pass to it a test data that hasn't been seen before, but we know it's normal. It's from the same distribution. And then we're going to pass to it after that also new data. So this is the data that we haven't seen. This is, think of it as future data coming in and streaming in. We're going to pass that in. Actually, that's where the fault had occurred down the line in that future data. Okay. This is just this one here is just a function to predict. I'm just putting it in a function so I can run it multiple times. So we're predicting and when I say predict I'm just talking about reconstructing the input signal. That's all what it is. So let's just kind of take a look at a few things here, just kind of visuals. So this right here on the test data, you can see that this is one sensor. I think it's a pressure signal, and it's a scale, so that's why it doesn't make much sense here. But you can see the blue is the actual signal, and then the reproduce signal from the autoencoder is orange, and it's there on that is pretty tight. So it's a fairly kind of close signal. We're able to reproduce signal pretty well. When I pass it new data, and you look here that I pass the new data, I have 2,000. So this is after on the bottom, the 2000 refers to kind of a couple of 2000 timestamps later. So we know that we had a fault at that point. And you can see on this bottom curve, the error between orange and blue is, you can see there's a difference. So the reconstruction error is starting to kind of get worse here. And you can see as you go further out, it's back to normal. So we have multi modes of operation on this particular equipment. So that we're seeing that one mode of operation is causing us some of those issues here. So there's some domain knowledge that goes into this space right here that I can interpret what it means. But the key thing to pay attention to is, I don't know if I can have anything here. It's this one right here, right? When we look at, thank you. So when I look at this delta right here, that's kind of what I'm interested in. That's what I want to train. I want to train a model on this reconstruction error, because what we expect it to see is when we see something like this, it's going to say that's unusual, right? So the one-class classification is going to learn that this is normal, this error between the orange and blue, and when we pass this kind of data to it, it's going to pick it up. That's kind of, in a way, what we expect to see here.
Why do you add noise to the?
If I don't, then I'm almost learning identity function. I don't want it to learn exactly what the input is. We do want it to learn the important features. So especially if we go into the high-speed data, you want to actually kind of pick up really the important features, just like you do in PCA when you say I want to do only 2% components or what have you. By actually adding noise to it, you kind of are shocking the system a little bit here, and you're kind of getting the features right.
How do you decide how much noise to add?
So that's a tunable variable. So if you saw in the presentation, I had so we leave that to people to say how bad was the data when you first had it. Did we have a lot of issues with the data? And you can decide how much noise. Part of that is actually we do put a guardrail on it, and that when I show the entire pipeline of optimizing the process, that kind of comes in. So it's a hyperparameter to tune. There's another one related to noise that I'll show here in a second as well. Okay. So here is our outlier detection method here. I'm passing it through a function. I'm using isolation force, so you can kind of see the isolation force right here. So this is where I mentioned the second noise kind of factor that I'm going to add here. This is called contamination factor. Think of it when you go buy a car, you go to a dealership, right? The second you drive the car out of your dealership lot, what happens to the value? It drops. The idea is that there's going to be inherent wear and tear that's going to happen. So if you have an equipment that you just overhaul or brand new, the second you run it, there's wear and tear. So that contamination factor is kind of a measure, an assessment of what that wear and tear. And again, that's a tunable number that somebody can kind of use and assess. So here what we're saying is about 0.5% of the data it has kind of degradation to it. That's kind of what we're saying. Okay. The rest here is just kind of passing the new data to it and fitting the not fitting predicting kind of and writing data back into a table and plotting it. So what I'm going to do is I'm going to show a couple of plots. So the first one here is I'm just taking two signals. It's just one way to look at this data here. If you recall in the PowerPoint, I showed a 3D visual. So that's kind of similar to this, but this is in 2D. So I got a pressure and temperature reading, or temperature and pressure reading, and just plotting them against each other. And then the way one-class classification works, you would have, like I said, one or either bad or good. Typically in scikit-learn, when you get 1, and which is in this case orange here, that's normal. -1 means this is basically kind of abnormal data. So not a surprise, most of the data is normal because we told it this is normal. We trained it on normal. This is on the training data. So if I pass to it the test data, we're still kind of getting similar thing. It's fairly normal, which we're expecting that. Now what we're going to do is we're going to pass abnormal data to it. So we're going to pass a signal that actually was normal for some point, and then eventually we actually start seeing kind of abnormal behavior with it. And this is kind of was actually a true event that had happened. What I'm doing here is I'm going to show only a pressure signal, and I'm going to have the x-axis as a time scale or timestamp. And what you look at here, it's going to go a little bit more. So if you look right over here, early on, up until like almost 2000, looked normal. I mean, we're not kind of seeing any outliers with it. But at some point here, we start seeing, or I guess 1000, we start seeing a little bit as we kept going on with more, right? Because like I mentioned, this is multi-mode of operations on this particular equipment. So it's different modes. So not all the modes were in kind of had the problem basically. And so we're kind of starting to see in here. And we actually did, that particular engine had a failure about a week later. So I'm not showing that here as well, but so we kind of saw that eventually we saw a failure on that engine. And so this is kind of what ends up, what you expect to see now. There's more work to be done from when we productionalize this, or it's the way the way it's productionalized. We don't run one single autoencoder. We run this. I mean, Dennis will probably tell you this many times, that you have to run it 20, 30 times, 40 times, and ensemble the results and do things like this. So there are kind of other techniques you have to do when you deploy this in production and give it to people to use, because we're not building it just for us and we're going to write code. We're going to give it to somebody who is not going to mess around with writing a single line of code. So there's some other kind of considerations to take. But you know, some of the I would say kind of setup and research has to go get done with this is, you know, doing things like this and checking certain events and assessing them. So I the presentation. Questions, comments?
The output was used for anomaly infection. You can try using this. The nodes in the middle.
Yep. So very good question. So the question is, let me go back up and just show what Dennis was asking me here. And I gloss over it, so this is a very important point. And this one right here, I'm basically taking the output. I'm taking the output from here, right? I basically said, give me the input, get the output, do a reconstruction error on that, pass it to one. Dennis is saying, well, you learned the features right here at that bottleneck. Why not pass that to and so we did, and it does kind of work in a similar way. And at 5,000 hertz kind of type data, I'm kind of windowing through it. I'm not going to be putting all that back as an output. But in a small dimensional setup, we would probably still go off the reconstruction error code. But yeah, so that's another kind of important thing that a lot of people would actually go after this middle layer right here. Yep.
Scrolling down a little bit.
Yep.
Reconstructed actual versus reconstructed.
Okay.
Earlier where you have some graphs.
Oh, I see.
Separation.
Yeah. Okay.
Yeah. So that second graph. So you're targeting the stuff on the low side where you start having a separation.
That's what I'm looking for. Yeah.
And then you're trying to train to be able to recognize that. Are you training just on the separation, or are you also including whether it's on the low side or high side?
No, it's just on residual. So I'm training it on this. So obviously, in some cases, this is gonna go higher. This is almost a year of data, and we said this is normal, right? There's wear and tear, but this is normal. I'm showing only just a small amount of that. And so obviously, sometimes it's something low. And that relationship. Remember, this is not just a single sensor; it's a multivariate problem. So the multivariate kind of residual is what we're comfortable with over here.
And
This is just one from one signal. I'm just showing up just to visualize one signal here.
As a domain expert, would you say that when there are faults, is on the low side?
It doesn't have to be. No. It depends on what you're looking at, which sensor you're looking at, or what kind of value you're looking at. So there's a lot of which sensors are actually contributing the most, and I'm not showing that here. That's kind of another thing that we have to provide to the analyst. So if you're an engineer looking at this and say, well, I know what a pressure should look like in this kind of condition, we want to show basically which sensors are actually contributing to the most to this kind of error. Yeah. Computational question, actually.
We're using Colab?
No, this is just on GitHub. Yeah. But you can train on Colab. It's super easy to train. It's an easy one. No, the computational from a different perspective. Go ahead. Yeah.
Are you considering the outliers in your training too, or just taking
no.
everything, or you're getting out of the outliers?
You don't train on outliers. You have to train. So the the core concept of this, when we say one class classification, is you train on normal. So it's a single class that we learn. It's an unsupervised method. That's kind of the idea. Is we actually, if we know what an outlier is and we have the signature for it, then we would build a fault detector. So you can imagine a softmax of classes of multiple different things, right? An example would be NASA, I think, been putting out some of that research work on the International Space Station. They have 5,000 simultaneous fault classification that they're doing. I mean, so that is different kind of problem. But here, so I'm not sure why there is an outlier. I don't know anything about the physics yet behind it, but we want to pick up when things are abnormal. And sometimes, you can guess like the highest rate of outliers is going to be bad sensor, something with a signal kind of going wacky. Yeah.
I did have a question about tangentially. So if you could talk about it, what the actual compute infrastructure looks like, because it seems like, or at least maybe what I inferred from it is this is kind of like on the edge, resource constrained, right?
Very good point.
So like a huge cluster.
Yeah. So kind of that's part of the choice of using autoencoders, because instead of if I'm doing data acquisition from vibration data and I want to do something on the edge, I'll happily use this right here. But any of that stuff, and I can do quick training. I would actually deploy a model that's already been trained, but put it there. This is actually not being used for the edge. So the way it's used right now, it's we have a pipeline that we have an NVIDIA setup. So it's training on the NVIDIA DGX, but then we bring it back to our platform, and that's when we serve it back up to the users. Well, the computational question that I mentioned here, and this is a fairly common thing with autoencoders. I mean, if you look at this one and those two, they're all the same network, they're same layers. So there's a method called to tie the weights of the layers. So I don't have to train basically 5 layers. I'll just train 3 layers, meaning those two and those two are the same, and just you cut the number of weights kind of almost in half. So that's kind of a computational thing to do. I didn't want to do it here. It's something I do in TensorFlow, not in Keras necessarily. But there's actually, I think in Keras, if you Google tie the weights of layers, there's somebody that's actually already put out like a class, PY class for kind of tie the weights. That's kind of a trick to pay attention to with this kind of method.
So if you add new sensor data,
Yep.
which maybe domain expert, they know that it's not related to the previous dimension. Do you have any empirical experience as in how many layers would you add in your autoencoder?
Yeah, so part of this setup is to define for certain equipment, certain level of sensors, you have this architecture. For the high-speed data, I would use a slightly different architecture than this, a little bit bigger architecture than that. So we have some kind of rules of thumb for that. I mean, more like a design of experiment setup that we tested different methods for. So yeah, you would not be using the same architecture for if you go to 100 sensors versus 5 sensors.
Using continuous data when it's
Yep.
What about like when they started the machine?
Yep.
The special
So
cases, it's different. Right?
Absolutely, yeah. So I mean, as you know, you don't just have deep learning or machine learning and poof, everything works. It's part of a software stack. So what I showed earlier, so the model, once it's deployed, it's actually we use I don't know if people are familiar with it. We use 9 for deployment. So we have like a large server license with them, and basically set up all the rules. So if I'm actually bringing any sensor data in, I'm checking certain things and triggering certain things before I actually do any scoring. So if machine is running, is offline or starting up, it's a transient mode, I'm not gonna be looking for that.
Have you had situations where you had to study that because you might
Yep.
like when I start the car, I get like some sound which is not it's running fine, but
Yep.
it's running.
Yep.
But at the beginning, there's something else you can catch.
Absolutely, yeah. So for that, the method of use is, though I'm not a huge fan. I've used them a lot, but I'm not a huge fan of the training that goes into it. Is LSTMs, because LSTMs on a transient mode, there's a lot of valves or things like that can happen. That think about your car, right? So there are certain things that are going to be activated in your car when you first start up the engine that are normally will run a different way. So you kind of want to pick up on those, and so it's a sequence of events that you have to pay attention there. And we're not going to use this. We'll have an LSM. So we've been working on some of those for startup in particular to look at, like you said, transient modes. Okay. Yes, sir.
I might have missed this, but when you look at your normal data for that one classification, is that just deliberately generated data, or is that just like a known example with 0 outliers?
Oh no, yeah, this is actual real engine data. And if you saw, it's going to be hard to go back to the PowerPoint. We had like this one interface set up for people. So we built user interfaces along with kind of plotting and all the stuff, so that people can look at it and say, I'm going to train this model on this data. So there's subject matter domain knowledge that has to come into that for now. That you can't just put in all data and train a model on it. There are some, you have to select what is normal. And so there is still a requirement. There's a human in the loop to actually get this right. Yep. All right. I think I'll leave that here.
So thank you again.
No problem.
Okay. Let's welcome our third speaker, Dennis. So Dennis is a senior consultant in modeling at Wood Intelligent Operations Group. He specializes in developing, deploying, and tuning of process simulation and numerical models for real-time production management. As part of these systems, he builds models for assets in energy industry, including wells, pipelines, and process equipment, and consults the clients from major energy companies. So welcome. You need this, right?
If you can launch this one.
This one?
Yeah, and then the second one also. Yeah, just in case you can launch the first link.
Yeah, it should work. It's still laying out. Yeah, I guess you need to.
Yeah, we can open the notebook on the GitHub post. Just a little bit faster. Open.
Is it a GitHub version?
Yeah, this one.
Okay. Okay.
Okay.
Yeah,
I can
think
try
this
from
should
here.
work.
Okay.
Yeah, it also works.
Good.
Yeah, I'm just wondering when you put this to this screen, I'm worried that this is not recorded on this screen. Can we? Just try once. Okay, so which monitor? This one, right? So it should be screen and monitor too. So we will have a 15 minutes break after this one, so I don't want to hold everyone for 3 hours long. Okay, so we can move this to.
Okay. Good. That's it.
It doesn't have. Yeah, I need to shrink it. Yeah, no.
Yep.
So I have 2 notebooks for today. One is called Deep Weather, and the other one is called Deeper Weather. let's see. Opens. Okay, so my name is Denis Zakharov. I am a consultant at Wood Group. Actually, it's called Wood now. And I'm also a core developer of a library called PythonNet, which is interop for Python and .NET languages, runtime. And also I'm a adjunct faculty at North American University here in Houston. I'll be teaching, I taught a machine learning course last year, and I'm teaching data analytics course next semester. This is the course, actually, the link, practical machine learning. So this talk will be about something I don't do at work. Like basically most of the work I do is confidential, except few presentations we made. But this is something that drove the applications of deep learning at work. So this was like the driver why we started doing deep learning. This is about weather prediction. So one thing interesting about weather prediction is that it's very general purpose application. The economics of actually weather forecasting it's used for insurance, reinsurance industries. It's used for transportation applications, agriculture, fishing. And in my case, we also use climate change and extreme event predictions. So this is a picture of airplane, and you see it's being hit by lightning. And there is a reason why I put this. Most of the weather data you can obtain is actually from the airports. It's public. You can obtain it very easy. Try scrolling. Okay. Oh, and by the way, this is a Colab notebook from Google. How many of you know Jupyter notebooks? Raise your hands. Okay. Oh, very good. So yeah, one reason why I use Colab is because you can switch between CPU, GPU, and also TPU runtimes. So I was not able to use TPU, but I was able to use GPU to speed up some of the predictions almost 10 times. This is a plot of different types of forecasting models. So this is from UK Met Office. And basically, you see that there is no single weather forecasting model, actually. Some of them, on the x-axis, you see some of them are predicting like within 2 days, and some of them are like within 100 years. And on the y-axis, you see some models have the grid of like a resolution of 1 kilometer versus like 300 kilometers. So, and there are reasons why they have so many models. But in my case, I'll be concentrating more on this in this region right here. So predicting very near future events, very local events. So how do you actually obtain this data? Oh, before that, if we have internet here, let me show you this. So this is a company, Yandex. It's like Google equivalent in Russia, and basically they copy all Google technologies. but one of these technologies is I haven't seen in the US is, oh, and then we get a lot of ads, of course. So, but one of the applications is weather prediction for taxi. So Yandex partners with Uber, and they provide taxi service, and so it's very important to have accurate weather predictions, and they developed deep learning based weather prediction model. Another recent breakthrough was so they use deep learning here in the US at National Energy Research Scientific Computing Center at 15 which is supercomputing, to identify extreme weather events. Okay, now we go into what I did here. So okay, so do we get it? Actually, there was a recent Kaggle dataset. You can now get it. It's 2017, and what I did was even before this Kaggle dataset, and the Kaggle dataset is only for 30 cities, so major cities in US and Canada, and few cities in Israel. But you can go to this website interface, Java stack errors sometimes. But basically, you request a data set for specific station, a specific time period, specific sensors, and they limit you on about like 1 gigabyte of data, and then they send it to you via email. So, that's very funny. Yeah. But yeah, here is the website. It's very hard to find it. If you just search like weather data, Google it, you will be offered a lot of commercial, but you can obtain it for free from government services. So okay, so I obtained the Houston dataset basically here, and it's very messy. So this presentation will be mostly about data cleaning, actually, not deep learning. So you can see stars and all kinds of variables, which I don't know what they mean. Okay, now you can see the size of this data set. Actually, this one is I'm using a few stations. I used a station from Houston, Austin, San Antonio, and Dallas, and Corpus Christi. And there will be a reason why I will explain later. So, okay, so what do we do with this data? We try to see what stations we have, how much data for each station we have. Next is, I actually forgot to get the Houston one. This is the one I wanted to predict, and then I got it separately. So I loaded separately. And then I concatenate these two data sets. Okay, next is, so next is we restructured this data so that we have basically time series, and then on columns we have two level multi-index. One is the variables, the other one is stations. And then we reformat dates, and then we can actually have HTML files also. They provide HTML files with metadata. So I loaded using pandas here to analyze what kind of information we have in metadata. And it's useful to, for example, see each variable. Let's see. Units from this metadata, and it becomes clearly, oh, okay, this is actually wind speed. Oh, this one, speed, and then dew point. You see temperature and so on. Okay. So next is when we read this data, it's all Pandas is reading it as all objects because it can't really distinguish if it's numeric data or text data or so on, because there are so many. But what I did is I pick a subset of data. So these are the variables I pick: direction, speed, temperature, dew point, altitude. Oh, actually, I don't know if it's altitude. Next is okay. So here we can do some plots. So this is a temperature major cities around Houston, including Houston, from 2015 to 2018. Actually, I also wanted to make sure that the data makes sense. And in the first notebook, deep weather, I have analysis of this data also, like to make sure that the dew point really makes sense with respect to temperatures and so on. So next is we want to apply deep learning, and this is actually based on the book by author of Keras. So he has a chapter on advanced usage of recurrent neural networks, this notebook, and I modified it quite a bit for this application, for my application. I think he originally used it for predictions on temperatures in Germany. So here, as we can see, we're just post-processing data, and then we basically subtract the mean and divide by standard deviation so that it's scaled properly around 0. And then after that, what we can actually do is as a quick check, this is very useful so basically we do a heat map of correlation between each variable, and this will show us if some of the variables are maybe redundant, or there is a very high correlation between the variables that should not be there. So next is actually the deep learning approach we're using here is recurrent neural network. And for recurrent neural networks, you need to feed time series data. And so that requires quite a bit of post-processing of regional data. So here, these are the variables defined. So basically, one of the most important variables is how back into the future we use the look back period for predictions. And then the delay is how far into the future we want to do the predictions. And then we also have a step size. So how many points, how frequent we want the data to be over time. The original data was every 15 minutes. And after post-processing, I got it to every 1 hour because of messy data. So basically, we can do predictions every hour. And now here, this is the generator that right from that book. So who knows what is a Python generator? Okay, very few hands. Okay, so I need to explain. So generators are really important for these time series applications because when you start post-processing your time series data, So you saw it was close to 1 million points. And then when you actually do also this look back, you add this look back, then you can get like maybe two orders larger data set in memory if you do it all at once. So what you have to do is that you have to apply a generator, and generator basically lazily will evaluate small subset of data and basically scan over time and push it to the training process without having all of the data in memory. It will not fit in memory if you try to do it with 1 million points. And
Dennis, can you apply it on images?
yeah, it doesn't matter. You can do that on images, time series data. Of course, you have to have at least few images in that generator set. Not like you can split the image into separate parts. So next is after the generator. So the generator creates us 3 data sets: training, validation, and test. Okay, this is looping a bit too fast. So, okay, for recurrent neural networks, there are multiple methods. So one of them is the most famous one everyone uses is LSTM, actually, a long short-term memory. And it's actually a very general purpose recurrent neural network, but it's also very computationally intensive. Compare it, for example, to convolutional neural networks, which can also be used for time series predictions, or even GRU. So in this case, we are using gated recurrent units. So this is like a simplified, more computationally performant version of LSTM. And there are multiple implementations of it in Keras. One of them, which is CUDA version, which runs on GPU, and it runs about 10 times faster. Now the issue with that, and we'll come back to that later. So, okay, so we run this, and then okay, let's see if we can predict the temperature. And this is we see the error over time. And so we see that the training loss is going down, but the validation doesn't go down much. And actually it starts increasing after some time, which means we can't really do good predictions. So then after that, I ran the same thing, but with the version on CPU. And the reason why I use the version on CPU is because of this very important feature of recurrent neural networks, a recurrent dropout. So what recurrent dropout does is it drops out some of the input data, and it does it so that it doesn't mess up the time series sequence. So if you use a regular dropout with a recurrent neural networks, it will not work. So you see this, I commented out. But now the recurrent dropout is not available in GPU. So this is a major pain point for a lot of people who are applying machine learning. So like you can use the recurrent neural networks on GPU, but then it's very hard to regularize them using dropout. And so PyTorch doesn't support, TensorFlow doesn't support, and any of the frameworks do not support recurrent dropout. Just the limitation of GPU.
You know if it's in the future, TensorFlow they can add it?
No plans in any of the frameworks. So if you really have issues with overfitting and maybe small data and you need to use dropout, then you have to run it on CPU. Another very interesting thing I found is actually even the training process is very different on CPU and GPU. And for our internal applications, we found that even LSTM has issues with like if you train it long enough, and if you try to run the same algorithm multiple times on the same device, same settings, everything same, you can have divergence of the error. Like you can have multiple solutions depending on how many times you run the algorithms. So there is like a joke, for example, for reinforcement learning, that it only works like, I think, like 30% of seats, or yeah. So basically, you have to also fix your seats a special way so that it works for some algorithms. And so we saw like completely different results depending on how you set the seats and things like that.
Is that with CPU or GPU?
So we saw it more with the GPU, but also couldn't fix it with the CPU. There are like there is seat in NumPy, there is seat in TensorFlow, there is seat in Python itself. You have to fix all of those, and then you also have to set to run only on one core, and then even after that we saw divergence.
So what do you do when you see divergence?
So actually, that's what Ziad suggested, and I haven't tried it. You can run. Actually, we did that, but we did some very simple version. You run like 10 times, you get 10 different versions, and you pick the median or some version of it. Okay, so basically, this is still work in progress. This is a very simple model, as you can see, GRU, and then these are the like predictions, for example. So I'm still working on improving this, and if you have any ideas, let me know. But so I made few improvements over the version in the Keras book. The author also had a lot of issues like this. So the improvement I made is, I think the biggest issue with applying deep learning for weather forecasting is that people use only one location, but and in that book he used only one location. But I think you need to use distribution of locations around that location, and that's, I think it's also time dependent. So like basically to have very good weather predictions, it has to be both temporal and also spatial. So that's what I'm working on right now. But this is something personal, and although we use weather predictions at work, we don't do this kind of stuff. It's basically only input for us most of the time, and we just interpolate. Yeah, if you have questions, let me know.
Right. So with more traditional like SARIMA type autocorrelation analyses, it's very important to identify additive outliers and level shifts. And that, those are those additional terms, and they greatly improve the models. Is there any attempt to do things like that? Because I see some places where it looks like there might be a level shift, and there might be some additive outliers in there too. Have we tried that approach of adding terms for level shifts and outliers, and see if that helps the RNNs as well?
So I haven't done like I haven't played with hyperparameters. Like basically, some of the key things I need to play with is like a look back period and the period to look ahead. But I'm not sure about shifts. So yeah, I mean, there is a lot of things that can be improved in this, and especially I think the cities I picked were just the ones for which the data was available. So I think there is a lot of improvement you can make. picking more geographically based rather than where the data is available. Yeah. So.
I feel like you may have gone over this, but what's on the y-axis here? Fiction.
So this is a predicted and target temperature, and I think in the first version it's better because I fitted it much more. Where is the slide
We
appear?
can move the browser.
Oh. So this is the version without special distribution. Yeah, I think it's still loading. Let's see. I can show. Okay. Oh. Okay. So no, not this. This is not prediction. So I think this is slightly better. So this is shorter period. So
this is a multi-step forecast, like how many time steps?
So this is looking ahead few time steps, which is like I think maybe let's see. So it's based on few parameters to look up. Here it is. So the step is 3, so I think it's every 3 hours maybe, and then delay 72. So this is the period into the future. So 72. So that makes 3 days in advance, maybe.
So how many days did you use? Like past days?
Look back. So 360 points. So that's like at least a few days, maybe a week.
Is there a specific reason why you didn't use cities east of Houston?
Reason why what?
You didn't use cities east of Houston, like most of the cities they chose are either north or west of Houston.
You mean like what? Corpus
Like, for example, if you chose New Orleans, it would be.
Oh yeah, because it's just I had to pick one data set, and you can only pick one state at a time. So there is no other good city east of Houston that you can pick in the data set. That's the only reason. I mean, Beaumont could be, but I also tried to be at least like 3-4 hours away from Houston. Too close is almost like Houston.
Can you try the same thing with a different city within your set? Like for his question, if you pick Austin, which is more central, did you get a different result?
Yeah, this is still a work in progress, and I haven't tried.
Since you already have the data set.
Yeah. I actually spend more time on data cleaning than doing predictions.
Dennis, did you try, what do you think of if you have one BCNN in front of an LCM or in front of a group? Have you tried that yet?
Yeah, so that's what I didn't discuss. So 2 things I didn't discuss is one is the future, which models we should really use. So I have a lot of experience with recurrent neural net. That's why I use them. But recent research shows that convolutional neural networks are sometimes even better for time series predictions, like stock predictions, especially people started using CNN. But also there is another direction, which is attention models. So these are models which auto-select what period and what points from the past we should use. Basically, it's like they are used for speech. Yeah, I mean another name for this is sequence modeling. So besides time series prediction, sequence modeling is also text speech predictions, and in text and speech they're using now attention models. So the core may be still LSTM or CNN, and then you have layers before that which filter out which points from the past you need to use. And the main issue with the LSTM and recurrent neural networks is that you cannot really fit 1,000 points. You basically, the linear algebra is so that you basically don't pick up any good signals anymore. Like you need to use maximum, the rule of thumb is maybe 100 to 200 sequences you can feed. After that, basically the optimization, the training process breaks. So that's why the attention layers help. With the attention layers, I think you can go to a few thousand sequences.
Talk about the length of the sequence.
Yes. So the few thousand will be like using past month of data to predict the temperature, which will be very good way to do it. But I mean, a lot of engineering is required to achieve that.
And even that book from Specially talks about adding 1D CNN to compress several thousand, sequence that's much smaller, and then pass it through.
Yeah, I think I saw like people combine. You can have the outer convolutional layers and then inner LSTM layers. That's also a possibility.
Okay, so let's have
One.
one question.
Just curious, how it's your prediction compared to the existing one? Like our cell phone is
I have no idea right now. So I think I'm not satisfied with these predictions myself right now. So I don't really want to do comparison. So this is still work in progress. I think the applications are huge, but there is no open source weather prediction model I have seen. So I think it will be a good thing for the public benefit if we have a good weather prediction model. Like Yandex model, I think it's private. I mean, they only provide the predictions, they don't provide the model.
I would suggest to extend the training set beyond the week, because sometimes we have a weather phenomenon that lasts a couple of days, 5, 7 days, focused on like high pressure systems that are sitting over here. So you may use your model, train the model only on those type, on those phenomena. If you go beyond the week, you may pick up different weather systems.
Yeah, and then we have to switch from RNN, GRU, LSTM to something which can handle a few thousand points. So for that you need a few thousand points, or you need to resample every 6 hours or so, but then you can lose some information in between. Yeah.
I don't know if I heard
Oh, you can use a GPU. It's just you cannot use one of the most important features of recurrent neural networks, which is called recurrent dropout. And the recurrent dropout helps with training a lot. Like I have seen, like with and without recurrent dropout, I can have very different predictions. And it's not just available on GPU. Basically, it's related to Boolean indexing. I think Boolean indexing is not possible on GPU.
Well, the reason I ask you this, so in the CUDA implementation of the recurrent network, it doesn't calculate the hidden state at each time step. When you do recurrent dropout, you need access to the hidden state at each time step, because you're dropping out you are dropping out units of each hidden state at each time step, because the GPU implementation doesn't calculate all the hidden units for memory efficiency, so you cannot do that.
Oh,
you can implement your own RN and then port and move that RN to GPU, and then you can handle it. But that means you need to write your own RN instead of using the CUDA optimized one.
Okay, we can have the discussion offline. So we again thank the speaker, Dennis. So we are going to have about 7 minutes break. So we will resume in 4:15.